Right.
via the APIs done by Fabric Manager, then this tool can reach them. But if the retimers are simple devices that do not want to participate, then it's hard to describe them.
And this is true for actually any device, right? Not necessarily. Retimer is an example, right? So you might have GPUs in a box. Not all GPUs are talking for their own. Okay, we need to move on. Okay.
Thank you.
Thanks.
Next, we have a great presentation by Tayu. I will ask him to introduce himself and the topic. Again, this track is based on 2 active projects within OCP, the server project and storage project. The sessions we have today are back-to-back. We don't have much break in between. Hopefully, we can go through them quickly.
Good morning, everyone. So a quick introduction about myself. My name is Tayu. I'm a system engineer at Meta, and I'll be pleased to speak to you today about more details on our next generation server compute platform. Now, before we dive into the details, I'd like to kind of ground the presentation around the goals for our next generation compute server platform, and there's 4 of them. First, we want to continue to improve our compute density in order to bring better efficiency into our fleets. Next, we want to be aware that power efficiency is also considered because we need to continue to scale our non-compute resources, such as networking, hardware, storage, and memory. Third, because we operate a variety of different types of applications and services, we want to have the flexibility to configure our hardware to better match our services workload in order to maximize our TCO. Finally, we want to have greater flexibility on where we can physically place our hardware in order to have better operational efficiency. Now, in order to meet these goals, we had to pull advances from 3 areas of hardware design. At the rack level, we will be using OpenRAC V3, which was disclosed in last year's OCP Summit. For the chassis, we'll be evolving our Yosemite V3 chassis to Yosemite V3.5. And we'll also be introducing a new server today called Crater Lake. So here's the highlights for each of these 3 elements. Crater Lake supports 4th generation Intel Xeon CPU, along with advanced DDR5 memory technology. In addition, Crater Lake supports up to PCIe Gen 5 endpoints, including support for CXL 1.1 devices. For Yosemite V3.5, it integrates directly with ORV3, and it's able to handle higher power server board designs due to the presence of higher RPM fans. And we also retain the same modular expansion options as found in the predecessor of Yosemite V3. OpenRAC V3 will allow us to scale up our power density at the rack level, along with better placement decisions that we can do with our power architecture, including power supplies and BBUs. and including the ability to scale up our BBU resources with the rack. Now, people might wonder, like, why are these goals important not only to Meta, but to just any other hyperscale applications looking to serve millions of users? So just to give a brief example, modern applications today are broken down into smaller services. Each of these services has specialized functionalities, and they must be independently scalable depending on business demands. For example, we might have a front-end service that's meant to interface directly with your clients, your customers, in order to provide the best-in-class customer service and experience. On the other side of the spectrum, you typically have your storage backend, which you might want to have different storage types, such as large objects like photos and videos, or smaller objects such as comments, lights, location, and time. And in front of your data stores, you might want to have some kind of caching to accelerate the access to data. Now in the middle here, typically is where your application logic ends. And in this area, typically we want to have multiple sources of input in order to produce some kind of output that's useful to your user. So by scaling our compute and power density, each of these tiers or services can be made more efficient. And when we have the flexibility to match the workload with our hardware config, because each of these workloads are quite different from each other, that's where we maximize our TCO. And finally, if we have the ability to use the same type of hardware configuration, but in different services, that's where we have operational efficiency. And I'll expand on that bullet in a little bit. Okay, so how are the products that I'm talking about today can realize these goals? So as an example, let's start at the server level. Crater Lake in Yosemite V3.5 retains the same modular expansion options as the predecessor, which is based on Delta Lake and Yosemite V3. That means at the server level, we can have various amounts of compute to memory ratio. We can append little to a dense storage, or even switch them out for some kind of acceleration. So to visualize these examples, you can have both a dense or lightweight compute option. If you want to take advantage of expansion, you can add a little bit of storage via E1S, or put a lot more storage in there. And finally, if you have some kind of needs for accelerate specific workload, the PCIe CAM expansion is a great option as well. Now with these types of different hardware server configurations, we can use them to build foundational building blocks at the rack level to help scale our applications. A few examples here is we can put a bunch of dense compute together for stateless compute racks. When we attach some storage to it, we can then use these to process ephemeral data sets commonly seen in caching or indexing services. We can put a bunch of dense storage in there to host large object stores. Switch them out for accelerators, and you can accelerate certain workloads. And finally, with OR V3's capability to help us scale up our backup power as needed, we can actually create storage rack types that's able to persist data locally and safely. And this is important to us because storage racks typically have additional power requirements at the data center level for power redundancy, as they typically might host sensitive or critical data sets. So you always want to have a level of redundancy there. But with ORV3 allowing us to decouple that, we can actually use these type of racks in more services and tiers without being tied to a specific location in the data center or even data center region. So this is how Crater Lake, Yosemite V3.5, and ORV3 help us build custom solutions that can help applications to scale. Now let's try to apply this back to our application example here. So you have your millions of users. For front end, because the users might grow with time or with events like New Year's and stuff like that, having these stateless compute rats can help you meet your demands as they fluctuate through certain events. Now on the storage backend, because sometimes you have to be able to manage multiple object types in different sizes, we probably have to use multiple hardware types here. For example, you might want to have dense storage nodes for your large objects. And for your smaller objects, where you don't need as much storage, you can use these persistent storage rat types. As far as the caching is concerned, these are typically more ephemeral data sets, and you can use the stateless ephemeral data rats for processing of those data. So in the center here, again, is our application logic. And as applications have become more and more sophisticated over time, we also see the same kind of dynamic that exists in the storage, where you might want to have more than one different types of hardware to handle your needs. And in this simple example, we could potentially have rats that's great for logic and data processing, along with servers that's handling your ephemeral data sets for indexing, caching. And you might even want to persist some data here so that you don't have to always go back to the backend, to your databases, your large objects to retrieve those data over time. So this is how, with OCP and the systems that we're introducing today, we can build these blocks to satisfy the needs of different applications. Now let's get into some of the more specific technical details on Crater Lake and Yosemite V3. So Crater Lake is a single socket 1OU server design capable of handling up to 165 watts of TDP for the 4th generation Intel Xeon CPU. As mentioned before, it supports up to 6 channels of DDR5 memory, and we have Gen 5 capable PCIe links to both the baseboard and the expansion ports. For the boot drive, we have a 22 by 80 M.2 slot, and we included a header if you decide to attach a platform root test module to it. In terms of the block diagram and architecture, this is actually very similar to Delta Lake, whereas like the DDR5s and the PCIe are attaching directly to a CPU. And the biggest difference here is actually in the upper right here, where now we have the ability to directly interface with the BIOS SPI flash via the bridge IC and BMC, whereas before we had to go through the PCH or CPLD. And now next, let's look at some of the changes at the Yosemite V3.5. As this is an evolution of Yosemite V3, there are slight changes here, but they are meaningful to us. Now we are supporting 15K RPM fans in order to enable the support of higher power or higher impedance CPU SKUs. In addition, in order to integrate with ORV3, our virtual power distribution board now supports 48 volts. At the chassis level, we're retaining the same blade to sled to chassis architecture of Yosemite V3. And in order to integrate the chassis to the ORV3, there was a slight height reduction. In addition, we added a vertical restraining feature in order to provide better shocking vibration in the Z-axis direction, and also support for a 48-volt power solution. Yeah, so Crater Lake and Yosemite V3 are two projects that were expected to contribute to OCP directly in this quarter. And we'd be happy to seek additional feedback and comments around these specifications before submission. As far as ORV3 goes, this project was previously talked about in last year's OCP Global Summit. Feel free to refer to that or to additional details in our meta engineering blog. Okay. So that's the end of my presentation today. We can take some questions here, or I'll be at the meta booth during lunch